Before I proceed with our next session, any questions with regard to PN junctions or any of the material presented so far, even the ones of last week? Any questions? I don't mind answering any type of question. Wala?
Sir,
Yes,
ask ko lang po sir for clarification po sir kung what is the major cause po ba kung bakit bumababa yung um, yung area po sir nung sa PN type po. Kaya po nagla-lower po yung isa. Dahil po ba para pumantay po yung Fermi levels nung
bakit nagbaband? Bakit nagbe-bend yung bands?
po sir.
Yeah, ang net effect is pumapantay yung Fermi level, no? But if you remember, I was explaining that before. Specifically pag hindi uniform yung impurity concentration, nagkakaroon ng migration from one side of the semiconductor to the other side. And because of this migration, nagkakaroon ng electric field. Dahil nagkakaroon ng electric field, nagkakaroon ng difference in potential energy, no? Because of the electric field. And that difference in potential energy is what actually causes the band to move. Naalala mo ba 'yon?
Okay po sir.
Oh, yun yung reason, no? Kung nag-attend ka nung lecture ko on non-uniformly doped semiconductors, because it's non-uniformly doped, nagkakaroon ng diffusion. Dahil nagkakaroon ng diffusion, nagkakaroon ng imbalance between yung charges between the left side and the right side. Magkakaroon ka ngayon ng electric field. And dahil nagkaroon ng electric field, nag-iiba ngayon yung potential energy for electrons between the left side and the right side, and that causes our energy band diagram to bend, ano? Because the energy band diagram is an indication of the potential energy of the electron, so that causes it to bend. So ganun din yung PN junction, dahil may P sa kaliwa, may N sa kanan, no? Nagmi-meet yung P at saka yung N. Okay? And then yung inaalisan nung N nagiging positive, yung pinapasukan ng electrons nagiging negative. So nagkakaroon ka ng electric field dun sa pagitan dun sa depletion region, no? So yung potential energy ng electrons nag-iiba, no? And that causes your energy band diagram to change, no? Tapos ang nagiging net effect nun nga, nagiging level yung Fermi energy. Pero yung Fermi energy only is level pag walang excitation, pag walang bias. This is only pag open circuited. No? That's what we call when there is no bias in a semiconductor, that's what we call thermal equilibrium. Kapag naglagay ka na ng mga voltage sources, hindi na yon thermal equilibrium. Pwedeng magbago na uli yung Fermi levels. So medyo napahaba yung explanation ko, no? But I hope that helped you.
Yes po sir. Bali, check ko lang po sir kung tama pagkakaunawa ko. Bali yung Fermi level po sir, nagpapantay po siya dahil yun lang po yung result ng diffusion tsaka electric field po. Bali ang mangyayari, magkakaroon po ng higher potential energy po dun sa isa.
Yes,
Tapos
dun
yung
sa
isa
isang
po
side.
bababa.
Dun sa isang side.
Apo.
So nagbe-bend yung bands.
Okay po. Bali in sa PN po na bali yung P po tumataas po yung potential.
Well, yeah, you can think of it as tumataas yung potential sa P or bumababa yung potential sa N. Kasi potential is relative, ano? Laging meron kang reference. No? Remember voltage? Voltage
Apo.
always has a reference, no? So depending on which you choose as the zero reference for potential, you either think of it as the P going up or the N going down.
Okay po, sir.
Any other questions? Sige. So today I'll provide you a short discussion on bipolar junction transistors. Yung BJT pinag-aralan niyo yun sa EEE 123, pero yung method of introducing the BJT in EEE 123 is its behavioral model. Dinescribe lang sa inyo the behavioral model of the transistor. So hindi in-explain sa 123 how it actually operates. So in this particular submodule, I'm going to try to explain to you how the transistor operates. So medyo mas malalim ng konti ngayon to kaysa yung natutunan nyo sa EEE 123. Okay, let me go to my prepared material. No? Okay. Okay, bipolar junction transistors. So dalawang klase yan. You learned this in 123. There's your NPN and there's your PNP. Although sa EEE 123, halos lahat ng examples na ginawa natin doon use the NPN. So dito sa 131, in addition to the NPN, you're going to have to familiarize yourself also with the PNP transistor. So yung mga figures natin dito sa taas, no, this one and this one, okay, these are simplified structures of the NPN and PNP transistor. What you have in an NPN is a P layer sandwiched between two N layers. Note that this is not drawn to scale. Itong P-type na naka-sandwich, this is actually really very thin. Very thin. And then sa PNP, it's the opposite. You have an N layer sandwiched between two P layers. So the left terminal we call the emitter. Okay, so this is the emitter region. The middle terminal we call the base, and this semiconductor is the base region. And the right terminal we call the collector. So this is the collector region. These are just simplified structures. If you take a look at an actual BJT, the structure will more typically look like this. This is what you call a planar bipolar junction transistor. The reason why it's called planar is because all of the terminals can be accessed from the same plane. So think of this as the cross section. This is a cross section. No? In other words, yung actual construction. So this is a cross section. Parang pag ganito yan, ano? If you take a look at it in 3D view. Okay. So this particular plane is where you access all of your terminals. So this is your emitter, this is your base, and this is your collector. Now, the transistor consists of two junctions. You have your emitter base junction and your collector base junction. So it consists of two PN junctions. Two PN junctions. Your emitter base. And then you have your collector base. So dito sa simplified structure na to, kitang-kita kung nasan yung mga junctions. So this is my emitter base, and then this is my collector base. Same thing here. This is the emitter base, and this is the collector base. When you take a look at the polar construction, okay, the junctions are as follows. So this particular junction here, that junction, that is your emitter base. Okay, and if, let me use a different color. If I take a look at now this junction here, that is your collector base. So notice that in a typical transistor, the emitter base junction is much smaller than the collector base junction. Your CB junction, this is larger than the EB junction. This is in a typical planar transistor. Okay. So this is my base region. This small part here is my emitter region, and this big part here is my collector region. Okay, these are our conventions for terminal currents. For an NPN, your current normally flows from into the base terminal. So if you take a look, it is normally flowing into the base terminal, into the collector terminal, and out of the emitter terminal. Again, no? Into the base, into the collector, but out of the emitter. For a PNP transistor, your currents are flowing into the emitter, but out of the base and out of the collector. So if you take a look, the direction of currents for the NPN and the direction of currents for the PNP are opposite each other. Kasi kung titignan mo, yung palabas dito, which is IE, papasok dito. Yung mga papasok naman dito, which is IB and IC, palabas dito. IB and IC. Now, normally, we draw the PNP transistor this way, with the emitter shown on top and the collector shown at the bottom. And we normally draw it that way because when you have circuits which show both NP and NPNP transistor, this would be usually sharing the same power supply. And if you take a look, the power supply is usually shown at the top. So that is why we normally draw the PNP transistor this way. But actually, you could have drawn it this way. No, you could have drawn it this way, where you show the collector, the base, and the emitter, and then you would now show the currents this way. This would now be I's of C. This would be I's of B, and then this would be I's of E. Okay. So this is one way of showing your terminal currents. This is the other way of showing your terminal currents. If you consider the voltages, let's consider the voltages. What are our voltages here on the NPN side? Okay, this is VCB, the collector to base voltage. This is VBE, the base to emitter voltage, and then what you have here is VCE, the collector to emitter voltage. Pag tinignan naman natin dito sa right side, okay, you're going to show this as VEB, emitter to base, VBC, base to collector, and then you have VEC. So if you take a look at the subscripts, nagbabaliktad yung subscripts natin. Dito we have VCB, but here we have VBC. Baliktad yung subscript. Dito we have VBE, but here we have VEB. And here we have VCE, but here we have VEC. So you're going to have to get used to the current directions and the shift in the subscripts whenever you're shifting from an NPN to a PNP. Take note that since charge cannot accumulate inside the device, okay, we can think of this as a supernode. No? You studied supernode in 1, 2, 3. You can think of this as a supernode. That means that the charges entering the currents entering the supernode must equal to the currents leaving the supernode. So that will follow KCL. So your emitter current in both instances, whether it be NPN or PNP, should be equal to the collector current plus the base current. IE is equal to IC plus IB. Are there any questions so far? So this is still a review of 1, 2, 3. Okay. Again, this is still a review of 1, 2, 3. What are your modes of operation? And I think I should be able to call out people to answer my questions here. So let's draw a table. Okay, so we have two junctions. You have your emitter-based junction, and you have your collector-based junction. What do we call the mode of operation when both of these are reverse bias? Anyone?
Cut-offs.
Sorry?
Cut-off.
Pag parehong reverse bias, anong tawag sa mode?
Cut-off, sir.
Yes, that's right, no? Is that Allen? Cut off, no? Cut off. Okay. Pag pareho siyang forward bias, ano naman yung tawag dun sa mode na yun, no? Can I hear from somebody else?
Sir, is that saturation mode?
Yes, that's
Sounds-
saturation, no? So this is forward. Pag when both your junctions are forward bias, you call that saturation. Okay, if the emitter base is forward biased and the collector base is reverse biased, can I hear someone else? What do you call this mode?
Active mode.
Yeah, thank you for the two that answered. So active, more specifically, they say forward active to differentiate it from, I will answer the next one, no? From if this is reverse biased and this is forward biased, you call this reverse active. Okay. So it's not usually used in this mode. Not usually used in this mode. The reason why a transistor might end up being in reverse active mode is kung nagkamali ka sa pagkabit, ano, napagbaliktad mo yung collector at saka yung emitter, so nagkamali ka sa pagkabit, and it ends up being in reverse active mode. So your transistor normally is only used in one of three possible modes: cutoff, saturation, and active. And these two are usually used in switching circuits. Or in digital applications, digital circuits. And then the active mode is used in linear circuits or analog circuits. Okay, in 131, we're going to go into each of these modes in more detail. But for now, dito sa module 1, I'm going to focus on the active mode. We'll focus on the active mode. So you're going to learn more about cutoff and saturation in module 2 when we take up the diode in more detail. Okay, let me draw the energy band diagram of an open circuit NPN. Okay, so if this is my NPN, and for this purpose, I'm going to use the simplified construction. This is just to make it easier, for us to visualize what the energy band diagram is going to look like. So this is my emitter, this is my base, and this is my collector. Okay. So my emitter region is the most heavily doped. This is usually the most heavily doped. Okay. The base region, this is very lightly doped. very lightly doped, and the collector, well, the case of the collector, usually it's between the dope, no, between the base doping and the emitter doping. So usually nandun siya sa gitna. Your base region is most heavily doped. Your emitter region is the most heavily doped. Your base region is very lightly doped, and your collector is doped somewhere in the middle. Okay, because I have two junctions, I'm going to have two depletion regions. So I'm going to have a depletion region here. Okay. Now, the depletion region in the base side is going to be wider than the depletion region in the emitter side. Can somebody guess why? Bakit magiging mas malapad yung depletion region dito kaysa dito? No? Let me redraw it, no, because baka hindi masyadong obvious sa inyo. No? I'll just redraw it. So usually ganyan yan. No? If you take a look at the depletion region, it will look like this. So the depletion region here on the base side is usually wider than the depletion region on the emitter side. Can somebody guess why? Anyone? Anyone dare to guess? It has something to do with the doping. Okay. Might as well answer. No. It has something to do with the doping. So if you will recall, this is doped very lightly. This is doped very heavily. So here, there are already enough electrons to occupy the holes in this area. Because if this is doped very lightly, okay, that means your hole density would be very small. So in order to cover all of the electrons here, you need holes from a larger space. And that's why the depletion region here is wider than here. So you expect the same thing here. So your depletion region here in the collector is going to be smaller than the depletion region here in the base. So this is your two depletion regions. So this is the EB depletion region. Let me just say EBDR. And then this would be, and then this would be the CB depletion region. Let me remove this because it might confuse you. Okay, so this is my base. Okay, so if this is open circuited, that is, there is nothing connected, there are no sources that are connected, I'm going to have two built-in potentials. So in my depletion region on the right, I'm going to have a built-in potential. The built-in potential is my P is going to be positive with respect to my N. Meaning to say, if I take a look at EC, this is my, let's just take a look at EC. This is the bottom of the conduction band. This is my depletion region. My EC is going to look something like this. Okay. I'm going to get some band bending here. Then it's going to go up. So this is going to be VBI, my built-in potential 1. Do you remember the formula for built-in potential? It is a function of, well, the formula for VBI, I'll write it again here, VBI is equal to KT over Q, which is V sub T, no? KT over Q ln of ND NA over NI squared. which is actually V sub t. We call this the voltage equivalent of temperature, KT over Q. No? V sub t ln ND NA over Ni squared. So that is your built-in potential. That's how much the band bends up. Okay, I'll ask a question. Where will, of course, here you also have a depletion region. Where will VBI be greater? Will it be emitter base or will it be collector base? Where will VBI be greater? Will it be the emitter base region or will it be in the collector base junction? I think the formula is a hint for you. Shall I call people at random who are here? Any brave soul?
Sir, emitter.
Yes, I heard someone.
Emitter, sir.
Where it will be great, yeah, it will be greater in the emitter base junction. No? Why? Kasi dito sa emitter, mas malaki yung value nung ND. No? Kasi yung value ng ND dito sa collector typically would be smaller than the value of ND dito sa emitter. And therefore, if you take a look at the built-in potential, it's going to be bigger at the emitter junction than at the collector junction. No? So if you take a look, that this is going now to look something like this. Where you have two depletion regions. Pangit yung pagka-drawing ko. Sorry. Where we have two depletion regions. It's going to look something like this. Okay, and then as I mentioned, the depletion region here is going to be wider than the depletion region here. So susunod din yung EV, no? So this is for EC, this is now going to be for EV. It's going to follow. So your EV is going to look this way. So this is now going to be your band gap or your forbidden band. The difference between the space, the energy states between EC and EV actually are empty, or to put it more accurately, there are no energy states between EC and EV. So this is the top of your valence band. This is the bottom of your conduction band. So this is for open circuited. Okay, let's take a look at what will happen now in active mode. No? So active mode, we said your emitter base is forward biased and your collector base is reverse biased. So let me forward bias my emitter base. That means that I connect a positive source, a source which is positive from the base with respect to the emitter. And let me reverse bias my collector base. That means now I connect the collector positive with respect to my base. So dito nakikita natin yung positive ng supply would be at the P, yung negative ng supply would be at the N. No? On the other hand, here we see the positive of supply will be at the N and the negative of the supply will be at the P. Okay, so these are going to be my depletion regions. Ang depletion region ko, mag-iiba ngayon. No? It's going to be affected by VBE and VCB. So what did we say will happen if we forward bias the junction? The forward bias of the junction will make the difference between will make that potential hill, will make that band bending smaller. Okay, so dati ganito yung EC. Let's just take a look at EC. Now, if I take a look at EC, it's going to be smaller. So it's going to be smaller. And then the reverse bias is going to make now the band bending larger. So this is going to be now larger. So if you take a look, this is going to be VBI minus VBE, VBI minus VBE. On the other hand, this is now going to be VBI plus VCB. And I have two depletion regions. The width, the effective width of my base region is going to be just this. That is where there are going to be charge carriers. Remember that in a depletion region, that is devoid of any charge carriers. You might say that N is equal to P is approximately equal to 0. Okay, let's try to imagine the flow of charges here. Let's try to imagine the flow of charges. Okay, when you have a forward biased PN junction, what does that mean? That means the current is due to diffusion. Okay, that was something that confused some of you last time. When you have a forward biased PN junction, your current is going to be due to diffusion. When it is a reverse biased PN junction, your current is going to be very, very small, and it's going to be due to drift. And because it's very, very small, for all intents and purposes, you might even approximate it to be equal to 0. That's why you say a diode only supports the flow of current in one direction. Okay, so your current is going to be due to diffusion. So what are the components of that current going to be? You are going to get holes diffusing from the P to the N. So I'm going to get holes diffusing this way. And I'm going to get electrons diffusing from the N to the P. So this is going to be electrons. Okay, so there are going to be two components of current, one component due to electrons and one component due to holes. So let's say this is my component of current due to electrons. Okay, and this is my component of current due to holes. Okay, the direction of the current is going to be in the direction of flow of positive charges. So this is the component of current due to holes. I'm going to call this I in my emitter due to holes, P. Note that if your electrons are flowing through the right, then your current component is going to be flowing toward the left, because current is defined as the flow as positive in the direction of flow of positive charges, or opposite the direction of flow of negative charges. So I'm going to get a current component here, and this is going to be I, okay, at the emitter due to electrons N. Now, this current, itong current na to, this is going to be very small. Very small. And the reason for that is, remember that this is very lightly doped. Yung doping nito, very, very light. And therefore, this current is going to be very small, especially when you compare it to IEN. Okay. In fact, later on, we will show that IEP is negligible. So this is going to originate here. No, that's going to originate here from the base, that particular current. Now, what happens with the electrons that flow from the left to the right? So meron akong electrons flowing from the left to the right. No? So you imagine your electron. Okay, this is by diffusion, and therefore expect that the energy, if it is flowing from left to the right, the energy will be higher than this particular energy. Let me draw this electron. I'll use a different color. So kunwari ito yung electron ko. Is my electron. It's flowing now this way. Okay. It's flowing from left to the right. Okay. Some of these electrons are going to recombine with the holes here and will form now part of the base current. So may component siya. Okay. So these electrons may component siya that will form part of the base current. No? Let me just draw it this way. No? Okay. So some of these electrons, again, some of these electrons will recombine with holes here and will form part of the base current. But W is very, very small. In other words, as the electron is flowing, there's a possibility. Remember, it's flowing from left to right. It is diffusing from left to right. There's a possibility that some of these electrons will actually reach this depletion region formed by the collector-base junction. Again, no, yung ibang electrons pupunta dito sa base, no? Some. In fact, very few. But most of these electrons will reach the depletion region formed by the collector-base junction. And when you have an electron, if I have an electron, for example, that hits here, that reaches here, this is going to be its kinetic energy. In other words, all of a sudden, this electron is going to move very, very fast. So as soon as it sees this hill, para siyang nahuhulog down the hill. It's going to move very, very fast and just emerge at this point. So from here, all of a sudden, it will emerge at this point. So that's going to be this current. So this is going to be, okay, this is going to be a current at the collector due to electrons. Okay. So, did you understand that? No? No. Let me just try to repeat that for emphasis. So these electrons will be flowing from left to right. Some of it will recombine and form base current, but most of it will go toward the right. No? And then it will be swept. It will be swept by this very strong electric field here, or very strong potential drop here. It will be swept into the collector, and that's why you call the collector a collector. Kasi parang sinasalo niya yung nanggagaling sa emitter. Okay, there's going to be another component of current. That's going to be a current that flows from the collector to the base. But this is going to be reverse saturation current. So there's going to be a reverse saturation current. I'm going to call this IC of O. So this is reverse saturation current. So remember, this is E sub C. Are there any questions?
Sir,
Yes, sir.
I have a question. Yung sa ICN, sir, since diba yung electron is papunta sa right, pero why is that, is it that yung ICN is going to the...
Yeah, if your electrons are flowing to the right, then your current, that means your current is flowing toward the left. No? You remember your
okay.
electrons, yung flow of direction of current is opposite the flow of direction of electrons.
I thought that was the due to electrons.
No. So
Yes.
but okay. Medyo nakakalito pag minsan, ano, because I'm describing the flow of direction of electrons, pero yung current is actually opposite that, ano. Okay. So anyway, let me continue. In fact, I'm taking more time than I thought I would. So if I take a look at IE, dito IE is equal to IEN plus IEP. IE is equal to IEN plus IEP. No? So this is my due to the diffusion of electrons and the diffusion of holes. No? But because the base is lightly dropped, very lightly doped rather, because base is lightly doped. Okay, IEN will be very much greater than IEP. Therefore, we say that IE will approximately be equal to IEN. So ito pwede na nating ineglecto because this is, as I said, very small. IE is just IEN. Now you have what we call the emitter efficiency. Okay, this is defined as sigma, and this is the ratio between IEN and IE. And we want sigma to be very close to 1. In other words, the ratio of IEN to IE, remember this is just approximate, no? We want this to be very, very close to 1. In other words, ideally in an ideal transistor, IE and IEN should be equal. Okay, meron din tayong tinatawag na base transport factor. Okay. Okay, this is the fraction of the emitter majority carriers collected at the collector. So if you take a look at this image, so ito yung mga electrons. What fraction of the electrons coming from the emitter will actually reach the collector? No? So remember, we said that these are electrons flowing from left to right. Yung iba sa kanila magre-recombine dito, no? Forming part of the base current. But some of this will be swept into the collector. So what fraction of this is actually swept and collected at the collector? This is what we call the base transport factor. So this is the symbol alpha T, and this is ICN over IEN. So ICN over IEN. And we also want this, to be very close to 1. Okay, finally, what we have what we call the transistor alpha. So this is the more. Okay, your transistor alpha is equal to sigma multiplied by alphas of T. Okay, so if we take a look at the formula, this is IEN over IE multiplied by ICN over IEN. That's right, no? IEN. So this cancels out. So you just get ICN over IE. Okay. And this is what you call itong transistor alpha. This is your common base. The reason why we say common base later on will be explained. This is called your common base DC current gain. Okay, note that IC is equal to ICN plus ICO. If you take a look here, this current IC has two components. That's ICN plus ICO. ICO is very, very small. Okay. It's very small, such that IC is approximately equal to ICN. So finally, okay, for simplification purposes, to simplify the computation, we just say that IC is equal to alpha multiplied by IE. IC is alpha multiplied by IE, where alpha is a number very close to 1 multiplied by another number that is very close to 1. So you multiply two numbers very close to 1, the product will be slightly smaller than either of the numbers, but will still be a number very close to 1. For an ideal transistor, your alpha is equal to 1. Now, you remember KCL? KCL applied to the transistor. From KCL, we said that IE is equal to IC plus IB. Okay. Okay, so we said that IE is equal to IC is equal to alpha IE. No? IC is equal to alpha IE plus IB. Okay, if I manipulate this, okay, I have IE multiplied by 1 minus alpha is equal to sorry. No, sorry, that's not what I wanted to do. No, let me erase this. Okay, IE is equal to IC plus IB. IE is equal to IC over alpha. No, if IC is equal to alpha IE, remember that IC is equal to alpha times IE. So you have IE is equal to IC over alpha. So this is IC over alpha is equal to IC plus IB. Or IC 1 over alpha minus 1 is equal to IB. Okay. Or what is this? No, IC 1 minus alpha over alpha is equal to IB. Or IC is equal to alpha over 1 minus alpha multiplied by IB. Ito ngayon, this is what is called the transistor beta. Beta is equal to alpha over 1 minus alpha. So itong formula to, naalala nyo siguro, IC is equal to beta times IB. No? I hope you remember that. Give me a hands up if you remember that formula. Yung IC is equal to beta times IB. Okay. And typically, okay. So typically you have IC, alpha will be anywhere from 0.99 to 0.995. Okay. If I get alpha over 1 minus alpha, okay, let me just do that now. No? Sorry. This is not 0.95, no? 0.95 to 0.995, no? But if I get alpha over 1 minus alpha, beta will typically be from 20 to sorry, masyado malaki ito. Ulit, no? Okay, again, typically alpha will be 0.95 to 0.99, no? Sorry. Wala yung slides ko. Okay, here. Typically, alpha would be from 0.95 to 0.99. No? So if you take a look at beta, if you use this particular formula, beta would be anywhere from 50, okay, to about kung 0.99, that would be about 100, ano? 0.01 over 0.99 over 0.01 100, no? But actually this is about 200, ano? So there's actually this 0.99x, no? Something like that, 0.99x. So beta would be anywhere from 50 to about 200. Are there any questions so far? Okay. So if you take a look at the characteristic curves of an ideal transistor, you have what is called your common emitter characteristic curves. Okay, what is this? This is a plot of IC versus VCE for a particular value of I sub B. So for a particular value of I sub B, your collector current will not be dependent on your collector emitter voltage. It's just going to be equal to beta times I sub B. So if this is my value of I sub B, let me call this IB1. So this is going to be beta times IB1. Then for a new value of IB, let's call this IB. This is going to be beta times IB2, where IB2 is greater than IB1, no? And so forth. This is IB3. This is going to be beta times IB3. So the characteristic curve of your common emitter, this is in active mode. Remember, this is in active mode. Is that your collector current does not depend on your collector to emitter voltage. It only depends on your base current. Okay, however, in an actual transistor, that is not the case. In an actual transistor, this will only happen for larger values of VCE. So initially, your collector current is going to start at 0, then it's going to go up, and then it's going to flatten this way. Okay. So this is going to be IB1, IB2, IB3. Okay. So this is beta IB1, this is beta IB2, and this is beta IB3. And then this is not going to be not completely flat, but with a slight upward slope. Later on, you're going to learn that that's what we call the early. And the reason why this is a slight upward slope is because as you increase VCE, habang lumalaki yung VCE, lumalaki yung difference nitong dalawa. Lumalaki itong hill na to, lumiliit itong W na to. Pag lumiit itong W na to, no, at saka lumalaki itong hill na to, then you get a slightly higher current collected at the collector. And that's why this will have a slight. Okay, if you recall from Shockley's equation, from Shockley's equation, your IEN is actually going to be proportional to VBE. No? Do you remember Shockley's equation? We took this up last time. So for a PN junction, you have I sub D is equal to I sub S e to the V sub D over V sub T minus 1. Eta V sub T minus 1. So if eta is equal to 1, then this is going to be I sub D, I sub S, e to the V of D over V of T minus 1. Okay. For normal values of V of D, e to the V of D over V of T will be very much greater than 1. And you can compute that. No? For example, V of D, let's say, is 0.7 volts. Alam naman nyo, yung voltage across the diode is approximately equal to 0.7 volts. No? Tapos yung V of T natin, which is at 300 degrees Kelvin. So let's just illustrate this. Ano? So at V of D equal to 0.7 volts. And then at 300 degrees Kelvin, V of T is equal to 0.026 volts. E to the V of D over V of T, this is going to be equal to, and I have my calculator here, yeah, it's going to be 4.9 times 10 to the 11. Ano? 4.9 times 10 to the 11. No? Ano ba naman yung 1 compared to this number? No? So, ibig sabihin nun, for normal values of V of D, your I of D is just I of S e to the V of D over V of T. Now, for the transistor, IEN will be proportional to VBE. That is your, I won't show it anymore. No? This is, in effect, this is like your diode current is going to be proportional to VBE, right? And in fact, the expression is going to be IEN is going to be approximately equal to, which is approximately equal to I of E, is going to be equal to I of S e to the VBE over V of T. So we assume here that eta is equal to 1. And this ice of S, okay, this is called your transistor scaling current. And the reason why we call it the scaling current is because this is a function of the dimensions of your transistor. And for silicon transistors, VBE will be approximately equal to 0.7 volts. So you have yeah, these are the important relationships that you need to know on the about the BJT. So you can have a model now of your BJT model. Okay, one model is this. This, by the way, this is for NPN, NPN. This is your emitter, as this is your base. This is your emitter. And then what you have here is, okay, this is your collector. Okay, so this is IB, IE, and this is IC. And IC is equal to beta times IB. Okay. On the other hand, you can also use this relationship, the relationship na to. If this is a VBE, so this is B, this is E, so this is VBE. Okay. Here, this is IC. Okay. This is going to be, yeah, ice of S e to the VBE over V sub T multiplied by or divided by, yeah, multiplied by alpha. Okay, multiplied by alpha. Okay, that's basically what I wanted to cover for today. Are there any questions? Probably a lot, no? It might take you a while to digest the information. Any questions? Anything that you want to clarify now? Wala. Okay, if there are no questions, then well, I'll stick around. No, those of you that want to leave already can leave. I'll stick around. I can afford to stick around for about 10-15 minutes. Those of you that want to ask questions, I won't close the session until everybody has left. So that's all for this afternoon. Okay, we're going to be starting a new topic next time, and the topic we will be discussing next time is a review of your devices, no? Because now we're into the physics, but next time it's going to be more device oriented. So that's all. Thank you.
Thank you, sir.
Thank you po,
Thank
sir.
you,
Thank you
sir.
po, sir.
Sir.
Okay, welcome.
Sir, pwede po magtanong.
Sure.
Dun lang po sa energy band diagram ng NPN.
Okay.
Kasi di ba po parang sinabi niya po nung una na high po yung built-in voltage sa emitter side. Tapos nung pagdating po sa active mode, bakit po ba't po naging mas malaki yung VBI sa collector side kasi tas nag-add pa po ng VCB.
Okay. Sa emitter side, so meron tayong emitter-based junction, di ba? And then yung emitter-based junction natin is forward biased. Kapag forward bias ang PN junction, hindi ba lumiliit yung bending ng band? Naalala mo?
Okay.
Pag if you have a PN junction, ano bang nagiging action ng bias sa PN junction? Kapag forward bias, lumiliit yung difference. Kapag reverse bias, lumalaki yung difference.
Okay.
Basically, yung built-in potential, liliit siya because of the forward bias. Lalaki siya because of the reverse bias. Okay, so liliit yung sa emitter-based junction, and that's what will cause the diffusion. Remember, hindi makapag-diffuse, no, dahil parang may potential hill, no. Pero pag lumiit yan, biglang nakaka-diffuse ngayon yung mga electrons into the p side, no, and then the holes into the n side. Doon naman sa collector base, lalaki siya, no. So lalong lalapad yung depletion region. Lalong hindi makakadaan yung kuryente.
Gets ka naman. Thank you, sir.
Yeah, sige. Okay.
Excuse me, sir. I have a question about last week's topic. Kasi,
Sure.
well, yes, I encountered something kasi, and I was wondering if my understanding was correct. If the Fermi level moves towards the conduction band, does that mean that the Fermi level increases?
The Fermi level is a fixed. The Fermi energy level is a fixed number. No, it's the value of energy where the probability that the electron exists is equal to 1/2. No, now that level adjusts depending on whether it is a p-type or an n-type. If it's an intrinsic semiconductor, that energy is equal to the midpoint between EC and EV. That is the energy level where the probability that an electron exists is equal to 1/2. Okay. But in reality, that energy level does not exist in a semiconductor because that's in the forbidden band. But theoretically, that's the energy level where the probability is equal to 1/2. No? Now, when you dope your semiconductor with donor impurities, the probability now becomes higher that your conduction band is occupied, and that's why your Fermi level goes up. And when you dope your semiconductor with acceptor impurities, your Fermi level goes down. I wonder if that answers your question.
Yes, thank you so much, sir.
Okay. No more questions? Mukhang wala na.
Thank you, sir.
You're welcome.
Thank you po, sir.
You're welcome. You're welcome.